Good day, everyone. We are Group 2, and our report will be the continuation of the topic Preliminary Treatment of Wastewater. And we will be discussing communitors, macerators, its types and uses, and as well as equalization. Now, two of the types of equipment used in pretreatment of wastewater are communitors and macerators. So before we talk about their description and uses, let's first talk about their role in pretreatment of wastewater. So during the preliminary treatment process, macerators grind the larger particles into smaller pieces to enhance treatment and removal. So this is also to avoid clogs and blockage. Then wastewater then flows to an aerated grit chamber where it is mixed with low pressure air to help settle out grit and other dense solids. And after the grits and solids are separated, partially dewatered and ultimately disposed of in a landfill. And after the initial treatment, wastewater flows by gravity to the flow equalization system. And as you can see in the moving picture in the side, that's a communitor, and the wastewater is flowing through there, and then the next stage will be the grit chamber. Now, what are communitors? So, communitors are devices that are used to macerate wastewater solids such as rags, paper, plastic, and other materials by revolving cutting bars. And they're most commonly used in small wastewater treatment plants with flows less than zero point 0.2 cubic meters per second. And these devices are placed downstream of the grit chambers to protect the cutting bars from abrasion. So this is like an added protection, and they're also used as a replacement for the downstream bar rack, but must be installed with a hand cleaned rack in parallel in case they fail. And communitors may create a string of materials such as rags that collect on downstream equipment. So because of this, and a high maintenance cost, newer installations use a screen or a macerator. So I think that's why communitors and macerators usually come hand in hand in pretreatment of wastewater. Now, what are macerators? So, macerators are slow speed grinders, and one type of this consists of counter rotating blades. And the material is chopped as it passes between the blades. The chopping action reduces the potential for producing ropes of rags or plastic, so this is usually placed after the communitors.
Next is we will discuss the types of comminators. The first type is a drum type. This unit featured a rotating drum with attached cutter teeth. Solids would get caught on and rotate with the drum and reduced as the teeth passed through a fixed comb. This design featured a large active screen area and heavy construction. The drawbacks of this unit's design included a bottom discharge that required a special L-shaped channel construction, trouble handling certain solids, the rotating drum was subject to wear from the bottom grit, and the teeth were complicated to remove to service. Next is a straight-through comminutors. The Worthington mixer, designed for straight-through channels, used oscillating cutters to sweep solids against vertically fixed stationary cutters, clearing a semicircular screen. While low maintenance with a straight-through arrangement, its thin, easily punctured screens pose a drawback. The unit had limited power and torque, struggling with heavier materials over time. Properly maintained, it had a solid reputation, but neglecting maintenance could impact performance. Third is the inline or grinders. The pipeline delamper was the first device to tackle the issues of straight inline solids reduction. This pressure rated unit was first created in the 1960s for use in the chemical process industry, but treatment plants soon found out great use for it. It might lower heavy solids directly in line and enhance the system's flow characteristics, which would lessen operator maintenance issues. The Delamper was the first inline processor to assist treatment plants in resolving a challenging and unresolved maintenance issue. Cutter cartridge enhanced twin shaft comminutors. By adding cutter cartridge parts, the original twin shaft design was enhanced. These cartridges have a single piece of solid cartridge material in place of several separate cutters and spacer discs. As a result, there are fewer tiny gaps in the need for stack retightening, increasing cutter strength. Twin shaft machines are frequently retrofitted with outdated individual cutter discs using the cutter cartridge concept. Inline shaftless design comminutors. The FMI Super Shredder utilizes a unique spherical rotor design with a central shaftless opening, combining low head loss from an open low configuration with high shear for finely ground output. This shredder features bidirectional cutting, robust handling of heavy solids, abrasion resistant hard faced cutters, and stainless steel construction. Excelling at high flow rates with minimal head loss, it maintains simplicity in maintenance with only two cutting elements. The design capitalizes on flow to aid in feeding, making it most suitable for applications with flow velocities exceeding 2 feet per second. The last type of comminutors is the high flow twin shaft grinders with diverters. Various flow diverters have been employed in twin shaft units to enhance flow by directing solids to the grinder while allowing flow to bypass it. The Geiger grinder introduced the diverter design in the 1950s, incorporating a grinder unit with a vertical rotating drum screen for handling high flows. In the 1980s, flat diverter screens like the disc screen and drum screens were reintroduced to increase flow capability. However, these designs has drawbacks such as pasturing or bridging of solids, screen wear, solid strappings, and the potential for solids to bypass the grinder. Drum type screens also suffered from reduced active screen area, leading to increased head loss. Next is the different types of macerators. The first type is the centrifugal macerators. Centrifugal force is used by these devices to break down solid materials. Solid particles are broken up and macerated by the centrifugal force of wastewater being driven through a revolving impeller. Second is the hopper feed macerators. The solid materials are gathered and fed into the grinding mechanism of these macerators through a hopper. Applications where solids must be manually or automatically loaded into the systems are appropriate for them. Next is the channel macerators. A channel macerator's main function is to reduce huge particles into smaller pieces so that they can be processed further. This lessens the chance of obstructions and harm to downstream machinery, including pumps. Next is the bar screen macerators. A bar screen is built into these macerators. Before the solid materials proceed through the treatment process, the shredders lowers the size of these particles that are caught on the screen. The last type of macerator is the twin shaft macerators. Twin shaft grinders employ two slow counter-rotating shafts with intermeshing cutter discs, initially designed for solid waste reduction. They effectively shear solids between the opposing cutters for dry solid reduction and feeding. However, when adapted for liquid waste systems, these grinders face challenges such as limited liquid passage, complex assembly due to numerous cutter and spacer discs, and the risk of cutter stack collapse and disc cracking due to interdependence among thin cutters.
Good day, everyone. I am Pauline Grace de Codera, and I'll be reporting the advantages and disadvantages of comminators and macerators. Several issues arise while evaluating the drawbacks of comminators and macerators in the context of water pretreatment, particularly about soaps and detergents. To solve these problems, a comprehensive strategy that takes into account the unique properties of the detergents and soaps in wastewater, the plant treatment procedures, and the constraints of the comminators and macerators is needed. for wastewater treatment facilities to effectively remove soap and detergent residues. Other treatment technologies, including chemical additives or advanced biological treatment, may be required in addition to these mechanical devices. To reduce the negative effects of these difficulties, constant optimization and monitoring are also essential. So here are the advantages in using the macerators and commonators. First is the particle size reduction. Consider a wastewater stream that has big solid detergent and soap residues in it. If these particles are not removed, they may cause problems for treatment procedures farther down the line. It would be possible to start the mechanical breakdown of these particles into smaller, more manageable ones by adding macerator or commonitor into the system. Second is prevention of clogging. In a wastewater treatment plant, dealing with high solids such as detergent and soap residues, the use of commonitors or macerators can prevent clogging and blockage of pipes and equipment. By installing these devices, the size of the solid components is reduced, allowing for smaller, easier drainage particles. This prevents clogging to ensure water flow, reducing operational interruptions and requiring less maintenance. These mechanical actions of these devices effectively breaks down the solid components, ensuring efficient and effective wastewater treatment. And the third one is enhanced sedimentation. Large solid particles, including fibrous components from household wastewater, are broken down in a commodity in a municipal wastewater treatment facility. These particles would adversely affect the sedimentation process in the next treatment step if they are not handled well. Next is versatility. The macerator's versatility is shown in its capacity to break down fibrous materials found in textiles and handle grit from manufacturing operations. Because of its sturdy construction and cutting mechanism, it works well in a variety of wastewater treatment situations and is adaptable enough to handle different kinds of solid materials that are present in the influent. Next is reduced pumping requirements. Both the commonitors and macerators contribute to reducing the size of solid particles, making them more pumpable. This results in decreased pumping requirements, potentially leading to energy savings because less energy is needed by the system to move the treated water through pipes. And lastly, for the disadvantages is the space efficiency. Macerators is known for their compact design and can be easily integrated into existing treatment systems without requiring significant additional space. This is advantageous for facilities with limited space. And for the disadvantages, first is the maintenance requirements. Continuous operation causes wear and tear on a commonitor placed in a wastewater treatment facility. Maintaining optimal performance requires routine maintenance such as lubrication and blade replacement. Delays in operations and higher costs might arise for not performing maintenance on schedule. Second is energy consumption. Macerators and commoditors use a lot of energy to operate since they have motors and other mechanical parts. Energy efficient alternatives are necessary because of these devices holds a high energy consumption, which becomes an issue in a facility trying to lower operating costs and environmental effects. And the third one is incomplete solid removal. Even though a macerator works well in dissolving soap and detergent particles, residues could remain. To accomplish total dissolved solid removal, more treatment processes may be required downstream if any tiny particles continue to exist in the treated water. Next one is the foaming issues. When a system handles wastewater that contains detergents, the usage of commonitors and macerators may unintentionally cause foaming problems. Detergent chemicals and mechanical effect might affect the foam stability, and precautions are needed or required to prevent and manage excessive foaming throughout the treatment process. Next is the chemical interactions. Chemical reactions or transformations can be triggered by the mechanical action of a commonitor on detergent chemicals. This might result in creation of compounds or byproducts that could provide problems for the following stages of the water treatment process, including difficulties with chemical interactions. Next is limited adaptability to changes in flow. The efficiency of comminutators and macerators may be impacted by sudden increase in flow rate or modifications to the influent wastewater's consumption or composition, notably the amount of soap and detergent present. The inability of these devices to adjust quickly changing circumstances may be an adverse effect on their effectiveness. Next is noise and vibration. Because commuters and macerators are mechanical devices, they produce vibration and noise, which can be problematic in some places where noise levels must be managed, such as residential areas. In order to satisfy regulatory and environmental concerns, it could be essential to use noise reduction methods. And lastly, environmental impact. Commonitors and macerators have an environmental impact that is influenced by the energy consumption as well as wear and tear. When it comes to wastewater treatment, a sustainable facility has to consider other technologies or methods to lessen devices' overall ecological footprint while also carefully evaluating and mitigating their environmental impact. So in conclusion, while commonitors and macerators are offer notable advantages in breaking down solid particles, including those from soaps and detergents. Careful consideration of their downsides is essential for effective water pretreatment and overall system performance.
Equalization in wastewater treatment involves balancing the fluctuating flow rates and pollutant concentrations in incoming wastewater. This process ensures a more consistent and manageable influent for subsequent treatment steps. Equalization tanks or basins are used to temporarily store and homogenize wastewater, helping to minimize variations in flow and pollutant levels. Equalization also plays a pivotal role in optimizing the overall performance of wastewater plants by addressing the dynamic nature of influent wastewater. Uses of equalization in wastewater treatment include flow smoothing, pollutant load balancing, pH adjustment, temperature equalization, and reducing shock loads. It also includes flexibility in operation and cost savings. In flow smoothing, equalization evens out the flow of wastewater, preventing sudden spikes that can overwhelm treatment processes. This aids in optimizing the efficiency of downstream treatment units. In pollutant load balancing, by averaging out pollutant concentrations, equalization helps maintain a more stable and predictable load for subsequent treatment stages. This enhances the performance of biological treatment processes. For pH adjustment, equalization facilitates the adjustment of pH levels, allowing for controlled addition of chemicals. This is crucial for ensuring optimal conditions for biological treatment and preventing damage to the equipment. Temperature equalization. For some wastewater treatment processes are sensitive to the temperature variations. Equalization helps moderate temperature fluctuations, supporting consistent microbial activity and treatment efficiency. Reducing shock loads. For equalization prevents shock loads by absorbing sudden increases in flow or pollutant concentrations. This protects the treatment system from potential damage and ensures a more reliable overall performance. For flexibility in operation, equalization allows for more flexibility in plant operation, accommodating changes in wastewater characteristics and influent patterns. This adaptability is essential for handling variations in industrial charges or seasonal fluctuations in domestic wastewater. For cost savings, by providing a buffer against peak loads and variations, equalization contributes to the overall efficiency of the treatment plant. This can lead to cost savings by reducing the risk of equipment damage, minimizing the need for emergency maintenance, and optimizing the use of treatment chemicals.
Hello everyone, I'm Clarice R. Benitez, and today I'm going to report about the types of equalization tanks. First is the continuous flow equalization tanks. So, continuous flow equalization tanks play a crucial role in wastewater treatment by maintaining a steady flow of influent through the system. So, these tanks are designed to even out fluctuations in flow rates, ensuring a consistent and uniform load on subsequent treatment processes. Second is the batch equalization tanks. So the batch equalization tanks are an integral component of wastewater treatment systems designed to adjust variable influent conditions. Unlike continuous equalization, these tanks operate on an intermittent basis, accumulating wastewater over a predetermined period before releasing it in batches. Next is the equalization tanks arrangements. So there are two types of arrangements. The first one is the inline arrangements, and the second one is the offline arrangements. So in the inline arrangements, all the flow passes through the equalization basin. It can be used to achieve a considerable amount of constituent concentration and flow rate dumping, and tanks placed directly in the main wastewater treatment process. And lastly, it ensures constant flow through subsequent treatment stages. So in the offline arrangements, only flow above the predetermined flow limit is diverted to equalization basin. So it used to capture the first flush from a combined collection system, and the tanks located separately from the main treatment process, and the wastewater accumulates in these tanks before being introduced to the treatment process. And lastly, it offers greater control over flow rates and loadings.
Once again, we are the Group 2 composing Hannah May Bacon, June Carlo Barosa, Selena Baizon, Clarice Benitez, and lastly, Pauline Grace Codera. And thank you for listening.